Thank you. So, thank you very much for the introduction. I'd like to introduce you to the topic Optical Process Control for Extrusion-based Additive Manufacturing in construction. And this is actually a student project I supervised and was conducted in the scope of my research project, which is funded by the German Research Foundation and is titled with the title Additive Manufacturing in Construction, the Challenge of Large Scale. So to give you a little bit of background, the topic evolves around the topic of additive manufacturing in construction. And I don't think I have to explain it in detail here because most of you have come in contact with that technology. So it's relatively new to the construction sector, but nonetheless, it's possible already to print houses with it. But unlike, it has a very positive outlook because we have these promises. We have fast construction and sustainable and automated construction that is promised by the technology. But unlike the picture suggests, it's not really that easy. It's the material handling is quite complex, and the whole process to control it is not super easy. And for that reason, yet at this point, it's not fully automated. So there's a lot of human supervision necessary. And that basically brings us to the topic, the optical process control. So to give a little bit more background, here's a bit of problem definition. When we have a lot of parameters that we have to set for the process. There is the extrusion rate, we have a certain nozzle size, we have layer height, and a lot of things. We also have different material properties. We have the climate that affects the printing, and all that can lead to different problems. For example, we can have under extrusion, over extrusion, we can have misprints, deformations, and even failures, like if the material is not fit for the speed of the robot, and also if the shape is not perfect and we are printing simply too fast. So the objective of this task is to develop an optical process control system to increase the reliability of the system. And basically, we focus mostly on the left problem statement here. Yeah, we implemented that system for a lab scale printing setup, which is used to print with clay. And we have a control system that is run with one control computer, which is a simple laptop or any kind of simple computer, which is connected to the control interface for the extruder via a module system and connected to the robot via Ethernet. And via USB, we also have a camera connected. Although this is a depth camera, we only use the optical camera detection for this process. So here's a little overview of all the processes involved. I will go into detail on every bit of it. So at the center of it, we do have the RTD control. This will be the topic of the next presentation. So if you have any questions, wait for the next presentation. For now, just think of it as a list of waypoints that is sent to the robot via TCP/IP connection. And with this connection, we can move the robot. But at the same time, we need to make sure that our camera system is able to capture the filament or the printed filament that the robot extrudes. So we need to also enable our camera to move along with the movement of the robot. We can use the same data to send to a camera mount system to control the position of the camera, which is done simply by taking 3 waypoints, calculating the angle, and then turning that into a stepper motor signal, which is controlled by Arduino. And then we rotate the camera into position so that the camera can actually focus on the filament in this blue bounding box. This works very well. So we made it into a very robust system to track the filament. And when we have that filament in the focus area, we can use image processing to detect the filament width, feed that information back to the RTD control, and then we can actually control the extrusion rate so that we fit the margin. As I see, there's a small mistake. The measured deviation should be below a certain threshold, so we can filter out any excessive controlling. So the whole system works on a PID controller, so we can also smoothen the whole control process, and it actually works quite well, as we can see in this moving image. So now I go into more detail on the optical dimension measurement. Our camera actually collects a image feed of 60 frames per second. We take every frame, every 60 frames per second. We segment it with an HSV filter based on the color gradient. Then we extract only the focus area. That's the blue box I showed before. We retrieve the contour on the target, on this small box, fit a rectangle, best fit to it, and then we measure that rectangle and convert it to a width value in centimeters. And then that is fed back to the system. We see the setup of the control system here. We have the extrusion nozzle on the bottom, the robot on the top, and in between we have the camera mounting that is rotating around the base. On the top here, we see a print without control. The surface below is actually a little bit tilted, so that's why it's kind of spread out more here. And we could eliminate that issue with the control system and have a very refined print with the control system. So that brings me to my conclusion. As shown before, we have our proposed system effectively tracks the system, the printed filament, and actually controls the process very reliable. This is basically, for now, it's very reliable on a single layer. On multi-layer, it can be difficult because of the segmentation process. The color gradient makes it difficult to assess a layer that is smaller than a layer below, because it has the same color gradient. And for that issue, we are planning to extend our system with a neural network detection method. And that will be it. I would like to thank you for your attention, and I'm ready for questions.
Thank you.